Okay, let's take roll. Percy is here. Urani, not here. Kilcrease, I thought I said, yes, I see Kilcrease's name. Lecky is here. Luna Sanchez, okay, is here. Macias is here. McKinnon is here. Morris is here. Powers is here. Renfro, not here. Salvador, not here. Spivey, is Spivey here? I don't see Spivey. Okay. All right. So before I begin, again, I have to apologize. I made an error, which I picked up on, and I checked the YouTube video, and I realized that I've once again sent you guys astray. Let me see if I can bring it up here. Come on. Okay, so let me go here. And it has to do with assignment number 3, if I'm not mistaken. I posted the answer here. Let me see. Assignment number 3. It's a minor thing, but I think it's still important. No, I'm sorry. Assignment 4. Not assignment 3. Assignment number 4, which I just posted this morning. The answer key. And oops, what is this? Okay, this should not be here. I don't know why I posted this here. Okay, let me unpublish that. Let me see if I have it here. I need to re-upload assignment. Okay, assignment number 4, answer key. So I'll do that later on today when I have a chance. So the mistake I made, if you look in your assignment that I've sent back to you guys this morning, you see that these 2 answers are switched, right? In your case, which is what I told you guys when I was introducing or when I was going through this problem. I went back to the YouTube video and I realized that I made a mistake, right? So please make a correction on that. I gave you guys full credit because it's my fault, but again, you know, make sure that you made a correction. The chloride or the sodium chloride would be the conjugate base in this case, and the carbonic acid would be the conjugate acid, all right? So I apologize for that again. So make sure you make that correction, all right? Okay, so what are we gonna do today? We're gonna talk about a very important experimental technique, which is used to basically analyze a solution by determining its concentration by reacting that solution with another solution containing another substance. And based on the stoichiometry of the equation for the reaction, you can determine the concentration of one based on the concentration of the other, all right? And there are different types of titrations. You have acid-base titration, which is what we'll be focusing on, I anticipate, pretty much for the rest of this class. Let me make this larger here. Full screen. Okay. But there are other types of titration too. You have redox titration. You have, which I think we'll talk about later on. We have, what's the other one? Precipitation titration. There are several types, all right? But they all have one thing in common. And that is that what you're going to do is measure a certain amount of one particular solution, right? And then you're going to add enough of the other until you get those amounts in terms of moles to be stoichiometrically equivalent. And based on that, you can determine the concentration of one based on the concentration of the other, all right? So that point where the stoichiometric equivalence exists for the 2 substances being added to each other, that's called the equivalence point, right? And basically in all forms of titration, that's what we're trying to achieve. We're trying to achieve that equivalence point in order to carry out a particular calculation. In the case of acid-base titration, and this is also true for other types, but since we're focusing on acid-base titration, in the case of acid-base titration, hold on, I didn't realize that this is in the way. Okay, so in the case of acid-base titration, in order for us to determine that point, the equivalence point, what we have to do is add a substance known as an indicator. An indicator is basically a dye, which takes on a particular color depending on the pH of the solution it's in, right? So therefore, what you'll find is that for most, if not all indicators, there is a pH range within which it will take on one color, and then if you add enough acid or base to change the pH, then the color will change to another color under which the indicator will display within a particular pH range, all right? So that's basically one important aspect of this particular process. Now, what you're looking at here is, and I wish I had the full picture here, but basically this is what you're going to need to carry out your titration experiment. And for those of you enrolled in my lab, you'll have the opportunity to actually carry out this particular experiment. So you're getting a bit of a foretaste of what you'll be doing. So there are different pieces of glassware which is needed. You're going to need your volumetric flask. This is where the reaction is going to take place. And even though this is not necessarily have to be the case, but typically we will put the acid in a volumetric flask, right? And what we'll do is measure accurately the volume of the acid solution, okay? The instrument that we would use to do that is called a pipette, and more specifically a volumetric pipette. So it's not one of those disposable pipettes that we're accustomed to, right? It's one that can measure accurately up to 2 decimal places when measured in milliliters, the volume of a solution. And they come in different sizes. Some of them are graduated, some of them are not. The ungraduated one just has one mark, right? And that mark represents a specific volume, right? So you can have a 10 mil pipette or a 20 mil pipette or a 25 mil pipette. I think the largest one I've seen is a 50 mil pipette, all right? So basically, I'm in the lab. For those of you enrolled in my lab course, you're going to learn how to actually pull the liquid up into the pipette so that you can measure that volume accurately. So what will be done in practice is that a certain amount of acid will be pipetted into this volumetric flask. Now, there's a long piece of glassware, it's cut off here, but there's a long piece of glassware that you're going to use, which is called a burette, all right? Let me see if I can bring up a picture of one so that you get a full idea as to burette. We have burettes in the lab, 50 mil burettes, but they come in different sizes again. Okay, so I want to see, there's one that shows you the graduation marks. Yeah, these are different burettes that are sold by different companies. I'm just gonna see if I can enlarge on this. Okay, it's not working. Let me go back. I've never seen these before. This is interesting. Poor man's burette. Never heard of that one. All right, let me just use this one right here. So let me see if I can get this to full size. Okay, I hope this is large enough for you in terms of, oh, okay, I can do this to magnify it. All right. So basically it's a long cylindrical piece of glassware, right? And you'll notice that the way it's graduated, I think what they did was that they took a picture of the top part here and the bottom part here. If you look at the way it's graduated such that you start at 0 at the top and then the volume numbers increases as you go down, right? So that's kind of different from what you're probably accustomed to, like, for example, using a graduated cylinder where 0 starts at the bottom and then the volume increases up top. And the reason why it's graduated that way is because you're using it not to measure the amount of liquid that is in it, right? You're using it to measure the amount of liquid that is dispensed from it, right? And again, for those of you enrolled in the lab, you're going to see how that works, right? The bottom part has a stopcock in this position, as you see, where it's parallel to the length of the burette. That's the open position. In other words, if you pour liquid into the burette, then the liquid will pass through the hole that is in the stopcock right here. So to close it, you have to turn it perpendicular, all right? And then the liquid will not pass through, all right? So I just thought I should show you a picture of that so that you have an idea as to what we're talking about. So basically what you're going to do in this whole titration process is you're going to add your sodium hydroxide. Again, it doesn't have to be sodium hydroxide. You could add your acid to the burette, but in this case, we're just going to add the base to the burette, the sodium hydroxide up to the 0 mark or near to the 0 mark. You're going to record that volume reading, and then you're going to put a certain volume of the acid in here. If you're going to use that 25 ml pipette, then that would be the volume of the acid you'd add it in here. And then you're going to add 2 or 3 drops of an indicator. As I said before, an indicator is a substance which takes on a particular color depending on the pH of its environment. Now, in the experiment that we'll be doing here in my course, the indicator that you'll be using is a substance known as phenolphthalein. See if I can write it down here. And the thing about this particular, hope I'm spelling this right. The thing about this particular indicator is that it's colorless in acid and pink in base. All right? So basically, when you have your acid here and you add 2 drops, this is your phenolphthalein here, add 2 drops of your indicator here, then the solution will remain colorless because it's colorless in acid, right? And then what you're going to do now, once you have set up everything, you have your solution in the burette, the base that is, you have your acid in the flask, you add your 2 drops of your indicator. Then what you're going to do now is slowly add your base, right? Until the solution here becomes pink. When it becomes pink, that means that the solution is just turned basic, right? So, and I'm going to stress this in the actual experiment that you'll be doing in the lab. You want to obtain or acquire the faintest pink color possible for your burette right here. I mean, for your solution here in your flask, right? So when you obtain that color, then you immediately shut off your burette, and then you're going to read the second volume reading on your burette. The difference between the two will give you the volume of the base added, and then basically you can do your subsequent calculations of determining either the concentration of the base based on the concentration of the acid, or vice versa, depending on what your task is at that moment. All right, so that's just a brief overview of the titration process. Now, the reason why I'm going through all that is because this is the process by which you can get data concerning how the pH changes as you add, in that case, your base to your acid, right? And what you're looking at here is a graph, a plot of the pH versus volume of base added for titration between hydrochloric acid and sodium hydroxide. So if you can imagine what I just described earlier, your acid will be in the flask, right? And then you start adding your base. So an additional part or an additional piece of apparatus that you'd have to add to the experiment to obtain this data is a pH meter, right? Where you stick the electrode in it and then you continually measure the pH as you add your base to it, right? So imagine this is what you're doing, right? You have your base in your burette, you have your acid in the flask. And from the look of things, because down here, when you add no base, the pH is 1, which means that the concentration of the sodium hydroxide is 0.1 m. So I'm just going to say here that the concentration of NaOH is 0.1. I'm just going to add a 0 here, m, right? Because minus log of 0.1 is 1, and that would be the pH before you add anything, right? Okay, so now you're adding your base. Now, I don't know what the concentration of the base is. I think it is 0.1 as well. Let me just check something here. Yes, it is 0.1. I'll explain why. So the concentration of the acid being added, or the molarity of the acid being added, is also 0.10 m, all right? Okay, so with that said, you're going to start adding your base, right? And what happens, right? As you add your base, the pH increases slightly, right? It's still acidic because the pH is below 7. Remember, below 7 is acidic, above 7 is basic, 7 is neutral, right? So you're adding your base, the pH increases until you get to what we call the equivalence point, which is the point at which, as I said before, you have the stoichiometrically equivalent amounts of both acid and base, right? So basically it shoots up to the equivalence point here, which is smack in the middle of the pH jump as you go from here to here. And then you add a little bit more base, and then the pH jumps to here, and then it continually increases and just continue to increase as you add more and more base, right? Now, the reason why I knew that the molarity of HCl is 0.10 is because the equivalence point is 25 mils, and I think they started off with 25 mils of sodium hydroxide. So I'm just going to say here that the initial volume of the sodium hydroxide is 25.0 mils, right? 25.0 mils. Okay? So basically, that's how you determine what we call the pH curve. We call this the pH curve, which is the plot of the pH of the titration solution versus the volume of whatever is being added. In this case, it's a base being added. So you're going to get that S-curve looking type of graph. Now, what we're going to do, and we're going to spend a considerable amount of time doing this, what we're going to do is learn how to calculate the pH at each point of the titration process, right? So it's a bit involved. And this, by the way, is the curve for a strong acid, strong base titration, right? We're going to see also what happens when you titrate, for example, a strong base versus weak acid, weak base versus strong acid, weak base versus weak acid, and so on, right? But this is basically the pH curve, the pH curve for the titration of a strong acid and strong base, all right? Okay, so before we get to the other types, what I've done is that I've printed some examples, which are not in the PowerPoint, which basically describe certain scenarios of this type and is asking for you to determine the pH at a particular point in this process. So let me hand these out. And for you guys out there in Zoom, I'm going to publish it. The same handout I've just given out to the students here. I'm going to publish it shortly. So let me do this. No, not that, this. Okay, so let me go to okay, where did I put it? Okay, so I put that particular handout in a folder called Extra Questions. And then I've published that right there. So this is the handout I just passed out to the class here. So you guys out there in Zoom can follow along, download it, and follow along as we go through each of these problems, right? So these are different questions dealing with acid-base titration, all right? So this question is asking for you to calculate the pH of the titration of, and it gives you several situations. The first of which is where you add 25.0 mils of 0.10 m hydrochloric acid with 15, you know what? Let me, I think, oh no, it's upstairs. I forgot, okay. I was about to add a Word version of this, but it's on my thumb drive in my desktop upstairs. So I'll just go with this. So, okay, so you have 25 mils of 0.10 m hydrochloric acid, and to that you're adding 15 mils of 0.10 m sodium hydroxide, all right? So this is the way you'd go about determining the pH of that solution. What you'll do is start off with calculating the moles of each, right? So I'm going to say here the number of moles of HCl will be equal to 25.0 mils, convert to liters. So you're going to have 1 liter over 1,000 mils multiplied by 0.10 moles per liter. And we work that out. So that would be equal to 25 times 10 to minus 3 times 0.1. Okay, so according to my calculations, okay, so according to my calculations, I got 2.5 times 10 to the minus 3 moles, right? And then we do a similar calculation for the sodium hydroxide. So the number of moles of NaOH is equal to 15.0 mils times 1 liter over 1,000 mils times 0.10 moles per liter. And this will be equal to 1.5 times 10 to the minus 3 moles. All right? So that once we have established that, then we write down the equation for the reaction between the hydrochloric acid and the NaOH. And of course, we know the products are sodium chloride and water, right? So we're going to set up an ice table. Initially, these are the amounts we're going to place under the respective reactants, right? So initially, we're going to have 2.5 times 10 to the minus 3 moles of HCl. For the sodium hydroxide, is 2.5 times 10 to the minus 3, no, 1.5 times 10 to the minus 3 moles of sodium hydroxide. Initially, you're going to have no sodium chloride and no water, right? So what's the change? Well, it's easy to determine which is the limiting reactant because it's a 1-to-1 mole ratio. And therefore, we can say that all of this will be used up. So this would be minus 1.5 times 10 to the minus 3 moles as far as the sodium hydroxide is concerned. The change for the hydrochloric acid would be the same, minus 1.5 times 10 to the minus 3 moles. And the change for the sodium chloride would be plus 1.5 times 10 to the minus 3 moles. And the water we don't need to concern ourselves with. And then at equilibrium now, we're going to find a difference between these two. So 2.5 times 10 to the minus 3 minus 1.5 times 10 to the minus 3 gives you 1.0 times 10 to the minus 3 moles. This will give you 0, and this will give you 1.5 times 10 to the minus 3 moles, right? Now, how do we determine the pH of the solution? Because these are what are left after the reaction is complete. Now, we can completely ignore this part here because the sodium chloride will not interact with water appreciably to affect the pH. If you remember, we said that sodium chloride is a salt of a strong acid and a strong base, right? Any salt of a strong acid and strong base will not have any effect on the pH of the aqueous solution, right? So any aqueous solution of sodium chloride will have a pH of 7, right? On the other hand, since we have hydrochloric acid left here, that would definitely affect the pH, right? So how do we find the pH? We need to find the concentration of H3O plus, right? Now the concentration of H3O plus will be based on the number of moles of the HCl, which is 1.0 times 10 to the minus 3 moles, and we divide that by the volume. So the question now is, what would be the volume of the solution? The answer is, you added 25 mils of HCl to 15 mils of sodium hydroxide, right? So that means the total volume would be, let me put it here, total volume of the solution at this stage would be 25.0 mils plus 15.0 mils, which gives you what? 40.0 mils, right? So the molarity of hydronium will be equal to 1.0 times 10 to the minus 3 divided by 40.0 mils, which we have to convert to liters. So multiply by 1 liter over 1,000 mils. And then we do the number crunching. So 1 times 10 to the minus 3 divided by 40 times 10 to the minus 3. And according to my calculations, this works out to be equal to 0.025 m, right? Which means that the pH of this solution at this point of the titration would be minus log of 0.025. And let's see what that gives. So according to my calculation, this works out to be equal to 1.60. So that would be the pH at this point where you add 15 mils of 0.10 m sodium hydroxide to 25 mils of 0.10 m hydrochloric acid. Okay, any questions about this? Any questions? Any questions? Any questions? Any questions out there in Zoom? Please feel free to participate. Okay, so is it okay for me to erase this? Can I clear this? Going once? All right. All right, so let's look at the B part. Same type of titration question, but the numbers will be different, all right? So in this case, you're adding 15 mils of 0.10 m hydrochloric acid to 25.0 mils of 0.10 m sodium hydroxide. Now, let's see if you can help me out here. Based on what we have covered so far, what would be the first step in this process? You can refer to what we did before. I'm sorry?
Calculating the moles.
Okay, so let's do that first for the hydrochloric acid. The number of moles of hydrochloric acid will be equal to what?
30.0 mLs.
I'm sorry?
Oh, I'm looking at something else, sorry. 15.0.
15.0 mils, which we have to
Convert to liters.
convert to liters, so 1 liter over 1,000 mils. And then times the molarity, which is 0.10 moles over 1 liter, right? So this would give 1.5 divided by 1,000 times 0.1. So according to my calculation, this works out to be equal to 1.5 times 10 to the minus 3 moles, all right? What next? Number of moles of sodium hydroxide, right? How do we do that? 25.0 mils, convert to liters, 1 liter over 1,000 mils. And then we multiply by the molarity, which is also 0.10 moles per liter. And this will give 2.5 times 10 to the minus 3 moles. All right? Okay, next step, based on what we did before. Well, okay, so the equation is HCl plus NaOH to give NaCl plus H2O, all right? Next step. Ice table, okay, so ice. So what would we put in the initial row?
1.5 times 10 to the minus 3 mole for HCl.
Okay, 1.5 times 10 to the minus 3 for the acid, and 2.5 times 10 to the minus 3 for the base, 0 for the sodium chloride, and we don't need to concern ourselves with water. Okay, so what would be the change? Minus 1.5 times 10 to the minus 3, because that would be the limiting reactant. And we're going to do the same thing here, minus 1.5 times 10 to the minus 3. And here we're going to have plus 1.5 times 10 to the minus 3. All right? Okay, so at the end of this reaction, you're going to have nothing here for the HCl. Here would be 2.5 minus 1.5 gives you 1.0 times 10 to the minus 3. And here would be 1.5 times 10 to the minus 3, right? What's the next step?
Concentration of each finds.
Okay, so to find the concentration of the hydronium, which is the same thing as the concentration of the HCl, right? That will be equal to the moles, which is, in this case, 1.0 times 10 to the minus 3. No, I'm sorry, not HCl. Actually, in this case, and this is a bit of a departure from what we did, so let me just erase this here. In this case, the only thing that is left that would affect the pH would be the sodium hydroxide, right? So in fact, what we need to do, since the hydroxide ion is the one that's going to be present at this point, what we need to do is find the pOH first, and then find the pH, all right? So we need to find the concentration of the OH minus, but before we do that, we need to find what? We need two things to find the concentration of OH. minus, right? One is the moles and the other would be what? Hmm?
Volume.
The volume. So how do we get the volume? Volume will be equal to 15.0 mils plus 25.0 mils. So that will be equal to 40.0 mils. And then we can calculate the concentration of the OH minus. I'm going to squeeze it here because of lack of space. The concentration of OH minus would be equal to the moles, which is 1.0 times 10 to the minus 3 moles, divided by the volume, which is 40.0 mils, which we have to convert to liters. So that would be 1 liter over 1,000 mils that you multiply by. Hope you can make out that, my scribblings. So that would be 1 times 10 to the minus 3 divided by 40 times 10 to the minus 3. And according to my calculation, again, this is going to be equal to 0.025 m. So we can find the pOH, which is minus log of 0.025, which is equal to 1.60, which means that the pH is equal to what? 14.00 minus 1.60. So that would be equal to 12.40. And that would be the answer for the B part, all right? So we have two examples here. One where at the end of the titration, you have only acid, or at that point. In this case here, at this point, you only have OH minus, all right? And as you can see, the pH varies. In the case of the first one, the pH is less than 7. In the case of this one, it's 12.4. All right, any questions about this one? Any questions? Any questions? Any questions? Okay, is it okay for me to clear this? All right, let me clear that. And let me scroll down to see what C has to offer.
Question on Zoom. Someone asked.
Oh, somebody else? Why can't I see it? Hold on. Okay, can you explain? Okay, so Miss Massey is asking. Okay, good question. She's asking, can you explain why in the first one we're looking for, I think she's talking about H plus ions, and in the second one we're looking for OH minus ions. Okay, so briefly, I wish I didn't erase both of them in order to answer this question, but let me try to describe what's happening. In the case of the first one, at the point of titration given in the question, based on the information provided, the only thing remaining at that point will be H plus ions, right? So therefore, we can directly calculate the pH of the solution by just simply using the formula pH is equal to minus log of H plus or hydronium ions, right? So that's what happens in the A part. In the B part, the only species that remains at that point in titration is hydroxide ions, right? Now the question is still asking for the pH. So therefore, since the question at this point, when we're solving it, since we have determined the concentration of the OH minus, then we can find the pOH and then subtract that from 14 to find the pH. All right, so that's the reason why we take a slightly different pathway in the case of the B part compared to the A part. So I don't know if that sufficiently answered your question. Okay, all right, good. So scrolling down, C, okay, let's see what C has to say. C is saying that they gave you 30 mils of 0.250 m hydrochloric acid and 25.0 mils of 0.125 m sodium hydroxide. Okay, so again, what would be the first step in this process? Based on what we have done so far. Moles of HCl, right? Let's do that first. So that would be 30.0 mils, which we have to convert to liters. 1 liter over 1,000 mils. And then we multiply by 0.250 m, which is moles per liter. And what does that give? Let's see here. 30 times 10 to the minus 3 times 0.25. So according to my calculations, this works out to be equal to 7.5 times 10 to the minus 3. Actually, hold on. Let me get the sig figs right. This should be 7.50 times 10 to the minus 3 moles. All right, so that's the acid. And then we do a similar calculation for the base. Number of moles of sodium hydroxide is equal to 25.0 mils We have to convert that to liters, so 1 liter over 1,000 mils. And then we multiply by the molarity, which is 0.125 moles per liter. So let's see what that gives. 25 times 10 to the minus 3 times 0.125. And according to my calculation, this worked for, is this right? Let me do this again. 25 times 10 to the minus 3 times 0.1, oops, 0.125. Okay, that's what I got. 3.13 times 10 to the minus 3 moles. All right. Again, please check behind my calculations to make sure I'm doing the right thing. Well, that's what I got. All right. Next step. What's the next step? Okay, so the equation, and we set up our ice table, right? So in the ice table, initially, we're going to have 7.50 times 10 to the minus 3 for the acid, and for the base, it's 3.13 times 10 to the minus 3. No sodium chloride, and don't worry about the water. And then the change would be what? Which one is lower? Hmm?
8.13 times.
This one right here, right? So this would be the change for that. This would be the change for the acid, which is the same. And here would be the change for the sodium chloride. So at the end of the reaction, you're going to have none of this. You're going to have 3.13 times 10 to the minus 3. And then for the hydrochloric acid, it would be 7.50 minus 3.13. No, what am I saying? 7.5 times 10 to the minus 3 minus 3.13 times 10 to the minus 3. And according to my calculation, this works out to be equal to 4.37 times 10 to the minus 3. All right, what do we do next? Let me continue up here. Well, now that we have the moles of hydrochloric acid present at the end of this process,
What is the concentration?
well, let's do what he said first. You need to find the total volume, all right? Which is 30.0 mils plus 25.0 mils, which would be equal to 55.0 mils, and then do what you said to calculate the concentration of H0 plus, which is equal to the concentration of HCl, and that would be equal to, what's the moles? 4.377 mole times 10 to the minus 3 moles divided by 55.0 mils, which we have to convert to liters. 1 liter over 1,000 mils. So let's see what that gives. 4.37 times 10 to the minus 3 divided by 55 times 10 to the minus 3. And the answer I got for the concentration, and please tell me if I'm correct or incorrect, but I got 0.795 M, right? We're not finished yet because the question is asking for the pH. So pH is equal to minus log of this number, 0.795. So let me see what I give. Oh, I made a mistake. This should be 0.0795. And the same should be here. Let me cross it out. 0.0795. Okay, so 0.0795, log of that. Okay, so the answer I got is, and please tell me if I'm wrong, the answer I got is rounded off to, okay, so this, since this is 3 sig figs, I need to round this off to 3 decimal places. So that would be 1.10. Right? And that's how that is done. Any questions about this one? Excuse me. Any questions out there in Zoom? Okay. Can I, no, that's not right English. May I? Clear this? Excuse me. Oh, somebody has a question? Oh, okay, thank you, Miss. Yes, all right, so let me clear this. All right, let's move on to D. Now, D is interesting because it turns out that in the case of D, the volume and the concentrations are the same, right? So let's see what happens in this case. So as usual, like we did in the previous three examples, we calculate number of moles of HCl, which will be equal to 25.0 mils, convert to liters, 1 liter over 1,000 mils, multiply by 25.0, multiply by 0.10 m, right? And that would be equal to 2.5 times 10 to the minus 3 moles, right? Now, because the molarity and volume is the same for the sodium hydroxide, that means that the calculation for sodium hydroxide is exactly the same and will give you the same result, right? So we set up our ice table. Of course, we have to write down the equation. All right. And then we start off with the initial row, which would be 2.5 times 10 to the minus 3, 2.5 times 10 to the minus 3, and this would be 0. Don't need to worry about the water. And then what happens as far as the change is concerned? Well, this is where we're talking about the stoichiometric equivalence, right? Where the amount of sodium hydroxide will react with exactly the same amount, mole-wise, of the hydrochloric acid. So what does that mean for the change? The change would be minus 2.5 times 10 to the minus 3 for both the sodium hydroxide and the hydrochloric acid. Oh, by the way, just checking my sig figs. Okay, my sig figs are right so far. Times 10 to the minus 3. And here the change for the sodium chloride is going to be plus 2.5 times 10 to the minus 3. So what would be the result of all this? No hydrochloric acid present, no sodium hydroxide present. The only thing that will be present at this point would be would be the sodium chloride, which would be 2.5 times 10 to the minus 3. All right? So basically, we're at the equivalence point where all the hydrochloric acid that is present will be reacting with the sodium hydroxide that is added at this point. All right? So what does that mean for the pH? There's no hydrochloric acid, there's no sodium hydroxide. The only thing that's present is the sodium chloride. And as we said before, the sodium chloride will have no effect on the pH of the resulting solution. So therefore, the pH of the solution would be equal to 7. All right? So that's what happens in the case of a titration of a strong acid and strong base, right? When you get to the equivalence point, the pH is 7. And in fact, that is what is shown in the graph that I showed you earlier. Let me show you. Oh, this thing is in the way. All right. Make sure you write that down and then I'll show you. I'll show you the graph. But basically, that's what happens in the case of a strong acid, strong base titration, right? When you get to the equivalence point, then that pH will be equal to 7. All right? Okay, any questions about this? Any questions? Any questions? Any questions out there in Zoom? Okay, can I clear this? Okay, let me do that. All right, so let me just show you the graph, which I showed you earlier, but I just want to point out that this is the graph I showed you earlier, right? Strong acid, strong base. The molarities are different, but still, well, compared to what we just, no, actually it's the same, coincidentally. So, and the equivalence point is at 25 mils of the base added, and the pH is equal to 7, right? So that's basically what you'll observe in any strong acid, strong base titration. All right, now let's, hold on. Are there any more questions? Oh, okay. So now we're going to get into a different type of titration. So before I get into these examples, I'm going to go back to the PowerPoint. So we looked at the titration between a strong acid, strong base. Now we're going to look at a titration between a weak acid and strong base, right? So an example of weak acid would be acetic acid, which I think is the example that is given in this, yes. Okay. Now, if you compare the shape of the curve that I showed you earlier to the curve, which is for the weak acid, strong base titration, there is one important difference. Let me just show you first the equations for the reaction. So basically what happens is that the sodium hydroxide will react with the acetic acid to form the sodium acetate and water. Now, the big difference between this and what we saw earlier in the case of the strong acid, strong base titration is that the sodium acetate will have an effect on the resulting solution, right? And that's because the sodium acetate itself here it is. The acetate ion itself will react with water, and the result will be the formation of the hydroxide ion, right? So basically, when you get to the equivalence point, basically what you're going to have present in a solution is basically acetate ions being present, right? Now, or I should say the base being present, the hydroxide ion being present at that point. Because the hydroxide is present at the equivalence point, what that means is that the pH of the solution will be above 7, which is different from what we saw in the case of the strong acid, strong base solution at the equivalence point. And in that particular case, the pH is at 7. But in this case, because we have a weak base, which is strong enough to react with water, you're going to have a basic solution at the equivalence point, right? So what we're going to look at in the examples that I gave you, number 2, is how do we calculate the pH of a solution at different points of this type of titration? So this question, let me go back to the assignment, not the assignment, but the examples. Okay, so this question says, calculate the pH of the titration of acetic acid by sodium hydroxide after adding 15.0 mils, and it gives you the molarity of sodium hydroxide, to 35.0 mils and 0.20 m of acetic acid. Okay, so there are some differences, but the first step would be the same as we did before, right? So if you remember, the first step would be what? Okay, so what's the first step? Okay, so number of moles of, okay, I'm going to use HA to represent acetic acid because I'm lazy, all right? So number of moles of the acetic acid would be what? 5.0 mils, which we have to convert to liters. 1 liter over 1,000 mils. And then what? Multiply by 0.20, right? M, mole per liter. Okay, and let's see what that gives. 35 times 10 to the minus 3 times 0.2. Okay, so I got 7.00 times 10 to the minus 3 moles, right? And then we do the same thing for the sodium hydroxide. Number of moles of sodium hydroxide is equal to 15.0 mils multiplied by 1 liter over 1,000 mils multiplied by, what's the molarity? Oh, 0.20, same as the acetic acid, 0.20 moles per liter. And let's see what that gives. So that is 1.5 times 10 to the minus 3 times 0.2. Okay, so according to my calculation, that gives you 3.00 times 10 to the minus 3 moles, all right? And then we set up our ice table. Of course, we have to write down the equation for the reaction. Sodium hydroxide plus the acetic acid to give Na A plus H2O. And then, like before, we set up our ice table. So initial values for the sodium hydroxide, it is 3.00 times 10 to the minus 3. For the acetic acid, that would be 7.00 times 10 to the minus 3. And this would be 0. So what would be the change?
minus 3.00 times 10.
Okay, for the sodium hydroxide and for the acid. Right? And the change for the sodium acetate would be plus 3.00 times 10 to the minus 3. So what do we end up with here? In the end, you're going to have no sodium hydroxide. You're going to have 4.00 times 10 to the minus 3. Here you're going to have 3.00 times 10 to the minus 3. All right? Okay. Now, here we have an interesting situation because unlike before, as I said before, the salt that was produced in the examples that we looked at before will not have an effect on the solution, right? On the pH of the solution. We cannot say the same thing for the sodium acetate. In fact, you should recognize that at the end of this reaction here, you're going to have two components or two substances in the solution. One is sodium acetate and the other one is acetic acid, right? And there is a special name given to a combination of a solution where you have a weak acid and the salt of that acid in that solution. What do we call that solution? A buffer solution, right? So basically at this point we have a buffer solution, right? And there is a way, or I should say there is an equation for calculating the pH of a buffer solution directly. What's that equation? Feel free to look in your notes. There's an equation that you can use to calculate the pH of a buffer solution. What's that equation? And you guys out there in Zoom, you can chip in as well, please. Feel free. What is the name of that equation? All right, hold on 1 minute. pH is equal to what? pKa plus
the
log of
sorry, the sodium acetate.
Okay,
concentration.
I'm just going to put A minus here. Concentration divided by?
HA.
Exactly, right? So basically, and this is called the Henderson-Hasselbalch equation. Henderson, just to remind you, Hasselbalch, not sure if I'm spelling this right. Equation, all right? So this is the equation you're going to use now to calculate the pH at this point. So there are two things, well, three things actually you're going to need. You're going to need a concentration of A minus. We have the moles of A minus here. You're going to need a concentration of HA. You have the moles of HA here. And you're going to need a pKa. And thankfully, they gave us the Ka value, right? Otherwise, you'd have to look it up. And of course, in your test, I'll provide tables, the same table I showed you in Canvas, right? Okay, now I'm definitely going to need some space here, so I'm going to do some erasures. Let me just erase this line right here. In fact, let me just erase all this here at this point. So, basically, to calculate the pH, that would be equal to minus log of Ka, which is pKa, 1.8 times 10 to the minus 5, plus log of the concentration. Oh, we need to find the concentration of A minus. Concentration of A minus is 3.00 times 10 to the minus 3 mole divided by the volume. What's the volume? 15, so we need to find the volume. So let me do that here. Total volume is equal to 15.0 mils plus 35.0 mils. So that's going to be equal to 50.0 mils, right? So we're going to put 50.0 mils here. Multiplied by, of course, 1 liter over 1,000 mils. So let's see what that gives. 3 times 10 to the minus 3 divided by 50. Okay, so according to my calculations, this works out to be equal to 6.00 times 10 to the minus 2 m. We also need to calculate the concentration of HA. I'm sorry for this looking so jumbled. So for HA, that would be 4.0 0 times 10 to the minus 3 moles divided by, again, the volume, which is 50.0 mils, multiplied by 1 liter over 1,000 mils. And that would be equal to okay, so according to my calculation, this works out to be 8.00 times 10 to the minus 2 m, right? So these are the molarities. Let me do some more erasing here. I'm just going to erase this part right here. Okay, so now we can plug everything into the Henderson-Hasselbalch equation. So pH, as I said before, is equal to minus log of 1.8 times 10 to the minus 5 plus log of the A minus, which is 6.00 times 10 to the minus 2 m divided by the HA, which is 8.00 times 10 to the minus 2 m. And then we do the number crunching. I'm going to work out this part first. So 1.8 times 10 to the minus 5, find the log of that. So this part here, and put the minus sign. So this part here is equal to 4.74 plus, and then I'll do the other part, which is 6 times, oh, this should be minus 2. It should be minus 2. So 6 times 10 to the minus 2 divided by 8 times 10 to the minus 2 equals, and then find a log of that, and that works out to be equal to, according to my calculations, minus, how many sig figs? Well, it should be 3 decimal places, so that will be minus 0.125, right? And then we do the addition, so according to my calculation, this works out to be equal to 4.6. .62. And that's how you do that. All right. So as you can see in this particular case, things are a bit different in terms of what happens at the equivalence point or at whatever point this is. When you're dealing with a weak acid titrating versus a strong base, compared to a strong acid, strong base titration. You have to take into account that the weak acid will convert, when reactive, will convert to a conjugate base, which is also weak, and that will interact with water to affect the pH, all right? Okay, any questions about this one? Any questions? Any questions? Any questions? Any questions out there in Zoom? Okay, let me clear this. And scroll down. Oh, okay, so this question is asking what is the pH of the solution at 1/2 equivalent and the equivalent point, all right? Now, oh shoot, you guys would have to help me because okay, this question is not that, it's not, okay, I'm going to assume something. The question didn't state this explicitly. I'm going to assume that we start off with the acetic acid in the flask and you're adding your base, right? Even though the question did not say that. So assuming that to be the case, can somebody remind me what the number of moles of the acid is? Hold on, let me scroll down. Okay, so the number of moles of the acid is what?
0.00 times 10 to the minus.
I'm sorry?
7.00.
7.00 times 10 to the minus 3 moles, all right? Okay, So what the question is asking for is the pH of the solution at 1/2 the equivalence point. So we're not at the equivalence point, but 1/2, halfway there. Now, because, hold on, let me scroll back up here. Because the molarity, let me see, are the molarities the same? Okay, the molarities are the same, so that makes life a bit easier, right? So basically, at 1/2 the equivalence point, the number of moles of the sodium hydroxide would be half. Number of moles of NaOH will be half of 7.00 times 10 to the minus 3 moles, right? So that would be equal to 3.50 times 10 to the minus 3 moles, right? So that's halfway to the equivalence point. So let me write this equation here again. I might not be able to finish this in time, but I'm going to try. Let me see, plus H2O. Okay, so initially, you're gonna have 7.00 times 10 to the minus 3 moles. Here, you're gonna have 3.50 times 10 to the minus 3 moles. Here, you're gonna have plus 3.50 times 10 to the minus 3 moles, right? So the change would be what? What would be the changes that would occur in this case? Minus 3.50 times 10 to the minus 3 here. Same thing here. And here you're going to have, oh, this should be 0. My bad. This should be 0. This should be 0 here. So here the change is going to be plus 3.50 times 10 to the minus 3. All right? Okay, so at the end of the reaction, what will happen? What will be the amounts of different substances left? You're going to have 3.50 times 10 to the minus 3 moles. Here you're going to have 0, and here you're going to have 3.50 times 10 to the minus 3 moles, right? Okay, now this is a very interesting situation because what we have here is a situation where, again, it's a buffer because you're going to have equal amounts, mole-wise, between the sodium hydroxide, the sodium acetate and the HA, right? So basically we can conclude, because they're in the same solution, we can conclude, and they're in the same solution, and the moles of them would be equal to each other. We can conclude that the concentration of HA is equal to the concentration of A minus, right? We could actually do the calculation, but I don't think that's necessary because I'm quite sure you can see that, right? The concentration of the weak acid, HA, would be equal to the concentration of A minus. So if we go back to the Henderson-Hasselbalch equation, right? If HA is equal to A minus, that means that these two will cancel out. So what does that mean? That means that you're going to have log of 1, right? And what is log of 1? 0, exactly. So what does that mean? The pH at this point is equal to the pKa, right? And therefore the pKa would be minus log of 1.8 times 10 to the minus 6, which would be equal to what we saw before, 4.74, if I remember correctly. Please correct me. I'm sorry, 10 to the minus 5, you're right, yeah. But the pKa is 4.74, right? If I remember correctly. From the previous, right, okay, good. So basically that's how you calculate the pH of this solution at half the equivalence point. And this is true generally for any titration halfway to the equivalence point. The pH that you would measure at that point is going to be equal to the pKa. All right? Okay, I'm going to stop here because I don't think I have enough time to complete I think there's a C part. Is there a C part? Oh, no, I'm sorry. There's another part to the B part, the equivalence point. Yeah, we won't have time to do that now. So first thing, next class, we will look at that. Now somebody's asking. Oh, okay, so she's asking, where does the 1.8 times 10 to the minus 5? That was provided earlier in the question. And in any case, if it's not provided, it's provided right here. And in any case, if you get a question where the KA is not provided, there's a table that I've showed you guys, which you'll have access to during your test, all right? So that would contain the dissociation constants of, all the weak acids that you might encounter, all right? Okay, so that's it. So next class, I'm going to complete this. Let me remind you of your test, which is next week, Thursday, right? So you have some time between now and then. And just to give you a heads up as to what chapters will be covered, it would be chapters 3 and 4. So 3 dealing with equilibrium. Just make sure I make a note of that to remember myself. 3 would be equilibrium and 4 would be acid and bases. All right. And I've sent you guys your assignment graded for those particular assignments. And I've also posted the answer key, which I need to make some changes. So I'll make sure to do that later on this evening. All right. Unless there are any questions, that's pretty much it for today. So I'll see you guys on Wednesday.
When's the test again, you said?
I'm sorry, next week, Wednesday, not Thursday. My brain. Next week, Wednesday is the test. All right, take care. Oh, somebody has another question? Oh, yes, Wednesday, Miss Macias. I'm sorry about that. Okay, for those of you guys, unless there are any other questions, I'm going to sign off.
I actually have one question.
Yes, ma'am.
You did send me like the graded assignment for, but it's not in the grade book. I mean, you sent me the email about the graded.
Oh, it's not in Canvas?
It's not in Canvas, so.
Let me see. Last name is Morris. Oh, you said test?
No, assignment.
Assignment. Oh, well, I have it in this grade book. I may have. Let me see. Morris.
It just hasn't come through on Canvas.
Oh, assignment 4. I haven't, for some reason, I guess it slipped me. I'm going to put the grades in later on today. Yeah, no worries. At least you have the graded work.
Yeah.
All right.
Have a good day.
Yeah, no problem. Okay, for those of you out there in Zoom, I'm signing off.